session today with Fred Koehler. Fred is an assistant professor at University of Chicago. Before that, he was a Motwani postdoc at Stanford. Before that, actually, he was here. So Fred has done a lot of really cool work in spanning kind of algorithmic and statistical questions in graphical model, sampling, high-dimensional statistics, robustness, and today he's going to tell us about unexpected test losses from generalization theory. Fred,
all right, thanks. Yeah, thanks for the introduction. Yeah, so this title, I was talking with Serbi before, and she thought that losses actually means it's like the loss, because like generalization theory, like, oh, maybe it's like you lose your sanity, for example. But so that's why I add this additional thing that is related to test losses. On the other hand, the title is still not, I think, very clear. So my hope is that the title will become clear by the end of the talk. But if it's not, yeah, please ask, because I think, yeah, it is not clear from the beginning. So yeah, another thing that's not clear, I think, to me is like generalization. Like we talk about, this workshop is about generalization. But then, yeah, what exactly is a generalization, right? Because we talk about lots of different things. And then I look at this picture, and then there's this robotic chicken, I guess, and then it's looking at some squares and circles. And I was trying to think, okay, well, this is clearly related to generalization. So just for fun, I posit like maybe generalization in the broad sense has to do with like, oh, you see things in the future, and then you have your past experiences. Like this chicken, I guess, has laid a lot of eggs, but now doesn't know if it's supposed to lay a square egg instead of a circular egg. And so I think this encompasses a lot of the meanings of what we say by generalization. On the other hand, there's like this very classical idea of generalization, which is like you have a training loss and test loss, like in my title. And that's what this talk is really about. Okay, so basically, what's the key thing is that in like classical generalization theory, we have examples which we learn from, and the crucial thing is that they're ID from the test distribution, so the distribution of future examples. And then I guess like a lot of the reasons that in this workshop, for example, we talk about generalization, but the test distribution is like different, like out of distribution, so on. But anyway, I'll focus on this, and then in this case, there's this other word of overfitting, and what does that mean? But like, basically, these are kind of like equivalent. And then overfitting here, I guess, broadly mean like the distortion between the training loss and the test loss, like your performance on your examples and your performance in the future. And so yeah, all these other things which are very important, especially these days, like OOD generalization, they're not strictly within the scope of classical generalization theory. So one could ask, like, why are we even talking about this? Because it like doesn't capture all these things that people really care about. On the other hand, I think it's a very natural mathematical setting, just to understand like what's the broader picture. We want to understand like how do we form patterns based off data, or inductive bias, all these kinds of things. And like in some sense, this is like a really good mathematical setting to study those questions, because like you avoid all the complications of these things. Okay, so that's our. Also, feel free to interrupt with any questions whenever. This is obviously just my vague thoughts. You could have a different opinion, of course. So anyway, yeah. Now I'll talk about like the serious mathematical content. So this talk is largely based off 2 joint works with a bunch of really smart people. So Lydia and Jen are both recent graduates from my department. Okay, let's see. And but actually, the more important thing. Not more important, but also important, is that actually, like what I'm going to talk about, like I would say it's like a new thing, but on the other hand, it's related to a lot of other interesting works and literatures, right? So, for example, people in various communities study things like applying statistical physics methods to understand high-dimensional statistics. There's a lot of interesting work on benign overfitting and like what's going on with that. There's like this idea of implicit or inductive bias, and so like what I'm going to talk about is like related to all these things. But I didn't want to, make the slides full of references and like pick and choose references. So the slides don't have a lot of references to all of these things that are going on, but we should be aware that it exists in this broader literature. Okay. And finally, I was debating whether to include this slide, but like for me, part of the motivation to give the talk, not just because Andre forced me to, but like also, when you submit the paper to NeurIPS or whatever, you write it. It's very, well, in this case, it's like pretty mathematically rigorous, like, has a lot of important technical details. And then you get back to reviews, and then, the reviewers, they're like, okay, we can accept it. But yeah, there's kind of this gnawing feeling that like, okay, like they saw the trees, but they didn't maybe get the forest. Like, and so I thought with the talk, hopefully it can bridge the gap so that it's kind of clear from my perspective what's like the higher level phenomena. Okay, but on the other hand, I think, like there's different styles, and like there's actually a lot of, if you really want things to be correct, there are a lot of important technical details. Like you can see there's some error terms and so on, which are actually, kind of important. So I'm just like throughout the talk, I'm just dropping all of these things, and they're actually not that complicated in some sense. Like they're all handled by the theory, but I'm just gonna not even, try to hint at what they are. Like they're not that important at high level. And also there's some, again, there's like some interesting minor technical assumptions, but I'm not gonna explain those. And yeah, so you can look at the paper to see the precise rigorous results, okay? And so yeah, still, I guess more high level stuff like, I wanna explain like two phenomena which can happen in generalization, which I think are not widely discussed. And they're best, or for me, they're understood by just like calculating some stuff in some very simple models. And I don't exactly know how it works if the model is more complicated. So that's what we're going to talk about. Yeah, you can, it's like a starting point, right? Like, okay, if you, in these simple models, like certain things happen. So in complicated models, probably related things happen, but I don't exactly know how it works in a more complicated model. Okay, so the phenomena one and phenomena two, they're both related to the title. Okay, so it's this phenomena of a mismatch between training and test loss. Okay, and so like if you study like a generalization theory in like a first machine learning theory course, we know when we talk about generalization, we often talk about generalization bound, and it's just something that says like the test error is related to the training error, but also something related to overfitting, some kind of measure of the complexity. And like, for example, simple things generalize better, complicated things generalize worse. Okay, and like when we formalize it mathematically, it's usually like there's some distribution. The test error is like the expected loss on the distribution over fresh examples, and the training error is the same thing but over empirical distribution. So like this observations we actually saw. Okay, and so that's the classical generalization bound. It kind of looks like this. And make a lot of sense because by the law of large numbers, if we fix the function, this is going to converge to this, right? So it's like kind of like just concentration inequality. It makes sense that we will be interested in such bounds. On the other hand, like, yeah, one of the big things I want to try to explain is like why we will look at inequalities of this form where the test loss is different from the training loss, okay? So here, there's going to be one loss function, like maybe tilde L or L sub lambda is what I'm going to denote it by. And actually, this guy that shows up in the test error is going to be different from the one in the training error. And I think it's kind of weird because by the law of large numbers, if we fix the function, like this is going to converge to this. So why would you change it to anything else? So hopefully, though, it will become clear, like why do we do this, okay? And I have some very, very simple example which will hopefully illustrate this point that the model could kind of by itself decide to change the function L that's showing up in the test error. And yeah, I think this is why I was saying like, oh, it comes from the mathematics. Like actually, yeah, it's kind of weird, right, to pick a different test error and training error. But if you try to understand generalization and you try to understand it like really precisely, like try to look at sort of optimal generalization bounds, then you are naturally led to this idea of having a mismatched training test. Yep.
Uniform deviation bounds.
Well, like the kind of generalization bound I'm going to talk about are what we would call uniform convergence bound. Like, so I think answer to your question is maybe no, but like, yeah, you have to be precise as to what it means. So like, for example, this is a one-sided inequality, right?
So
yeah.
the loss can be higher.
Yeah, it's a one-sided inequality. And then like when you look at optimal generalization bound, it's very important not to try to prove, or the two directions of the inequality behave differently. Yeah. So it would be very important to look at one-sided inequalities.
Yeah. I think you mentioned this earlier, but just to confirm, so throughout the rest of the talk, we should assume that the distribution of the test and training.
Yeah, they're always going to be the same. Yeah, okay. That's right. Yeah, so we're not doing added distribution. Okay, so that's phenomena one. And so not clear yet, I think, but hopefully will become clear. And then phenomena two. Okay, so I like this terminology, implicit bias of overfitting. So this is from a title of a paper by Ohad Shamir. And then, yeah, there's this related idea, which I'll try to explain, of like these emergent losses. Like, it's not, you just have some model, you train it, and then it's actually not obvious that there's like this hidden test loss. We can calculate what happens. And like broadly speaking, yeah, what's implicit bias? Well, there's a lot of work on implicit regularization, right? So it's like, you have a model, you train it with some particular optimization method, like a gradient descent, near descent, and it leads to certain implicit effects on the regularization of the model. So the learning algorithm prefer to pick models which are simple in a certain sense. So that's the field of implicit regularization. There's a lot of interesting work in this. And then the new phenomena, which is related but different, is that like actually basically the model capacity or the amount of overfitting in this talk is going to lead to changes in the loss function, right? So it's related to what I said in the first slide. But yeah, this is important because when you optimize different losses, generally speaking, you expect to get different solutions, okay? And then, yeah, right after this, I'm going to go through this like embarrassingly simple example that will explain these points. And then later in the talk, I'm going to show some examples where you can calculate what this like sort of emergent loss is, and it would be some kind of not obvious function in general, but it will have this nice mathematical property of being square root Lipschitz. So the square root of the loss will be Lipschitz, and yeah, we'll get there, but that's where we're going. Okay, and so here's an example to illustrate the idea. And the example is, it's going to be kind of stupid or like unrealistic. But I just try to make the example as simple as possible so it's clear what I'm trying to illustrate. Okay, so I thought it helps to have a story, but the story, it's not like real life. Okay, so here's the story. So you have some data, like maybe you're a company, and you have the data, and then you're like, what do I do with data? It's like, well, surprisingly, what you want to do with the data is use it to make money. Okay, so that's a step 2. And then what's step 3? Well, okay, here's the example. It's like you want to use your data to target ads. Something that's useful for targeting ads would probably be the income level, right? So like you don't want to advertise like a really expensive car to someone who doesn't have money to buy the car, right? So okay, so then and you're like in the real world, okay, you might want to solve problems like this, and then you have information about users. So generally speaking, what you might do is train a model to predict, say, the income or other target feature of interest based off the data which you actually do have. Okay, so that's the made-up story. Yeah, if you think really seriously about it, there's lots of additional complications in real life, but I thought it would be helpful, okay? And so let's continue the example. And so, yeah, naturally, you want to train a model to predict income, so it helps to actually get some data, like, for some small set of users, maybe you can actually figure out their income. And so here, this is just an example, like I actually have some income data, and like these are just the incomes you observe, okay? And now we want to train a model to map our features to the target Y, the income. Okay, and then how do you do it? It's kind of like machine learning 101 or statistics 101, like probably try to minimize some loss. So let me try to minimize the L1 loss. And we can talk more about why L1 loss, but in this case, it would be a good choice. And then, yeah, like I said, to make the discussion clearer, like I'm just going to consider like a very idealized setting where you have features. And like the bad news is that they're independent of the target. Okay, so it's not important. Like when I talk about the general mathematical results, it's not going to be important that the features are independent of the label, but it's going to make the illustration in this example much even simpler if I assume this. Okay, so your features are useless, and also for simplicity, I fit linear model. Okay, and so yeah, here's you do it, and then here's you check the performance on the test set. There's no correlation, right? Because the features are independent of the label. So you see, you get really bad predictions. Okay, so that's kind of not exciting. Okay, and then for some reason, I decided to include a picture of this guy. So here's a trivia question. Does anyone know who this guy is? It's like a little bit related. Okay, so yeah, this guy's named Murphy, and then he has Murphy's law that like anything that can go wrong will go wrong. And so this is an example, like, oh, you like try to predict something, but turn out your features are really bad. Okay, so it's not directly related, but just for fun, okay? And now here's the question. So that was kind of not interesting. Like your features are bad, your model is bad, right? So nevertheless, I think there's something that kind of interesting that can happen even in this really simple model. And so to explain this, I'm going to show you some plots. So to explain the plots, I want to tell you exactly what I'm doing. So yeah, we're training linear models. And then there are some things we can choose, right? Like the level of ridge regularization, okay? And I'll just fix the number of examples as 200, okay? And obviously, because the features are uncorrelated with the label, the only part of the learning which is like kind of useful is the intercept, actually, right? Like compared to like not knowing anything, at least the intercept tells me something about the true world, okay? So that's the only useful output of the learning is actually the intercept. And so what I'm going to do is I'm going to plot the intercept for different levels of regularization. And then you can think to yourself, like, what's it going to look like? And it's actually going to, the plot's going to be relatively simple. And so maybe you can or cannot guess what it will look like, but this is what it looks like, okay? So, you know, I imported CVXPy and then I trained the model and this is what I get, okay? And so on the x-axis, we have the regularization string. So here, not much regularization. Here, there's a lot of regularization. And here's the intercept B, okay? And you can see here, the intercept is much higher than over here. And there seemed to be some kind of smooth transition between these two, okay? So, I mean, you expected something to happen. Okay, so this is what happened, okay? But, you know, as I explained, like mathematically, you could have guessed this is what happens. And so, okay, that was like one experiment. But let's do another experiment. Oh, go ahead.
Why did you import CVX.py?
CVXPy. Oh, to train the model, it's like an optimization.
Why don't you just invert a matrix?
It's L1 loss. Yeah, right. Yeah. So if you're, yeah.
Run like.
Oh yeah, this is practical advice though that like CVXPy is a really good package. Like if you can use CVXPy, I would highly recommend it. Like turn out it works really well. Yeah.
Not a joke.
Yeah, that was not a joke. I actually use CVXPy. Yeah, whenever it's convex, check out CVXPy. High quality software package. Yeah. What?
Like, because B is predicting the main income, right?
Oh, okay, good. So I think, yeah, I think you're kind of guessing what's happening. So this number is kind of close to the true mean. Yeah, that's actually what's going to happen. Yeah, so that's why I said it's actually possible to predict. You know, in a lot of times in life, you just do stuff and you get outputs. But in this case, you actually could have predicted what happens. Okay, and so yeah, let's do another experiment and then we'll discuss more about what's going on. So regularization level is one way to control model capacity, but it's not the only way. And then another natural way is to control the number of parameters of the model. So here I'm sweeping. So here I just ignore all the features. So I only have the intercept. Here I use all of the features. So in this example, just arbitrarily I have 800 features, okay? And you know, among other things, you can see that as you sweep the model capacity, you get kind of a similar thing that happens where like this point is very similar to the endpoint here, and then the endpoint here matches the endpoint there, okay? So yeah, they're just two plots, okay? But there's some meaning to the plots, okay? So here they are. You know, it's not like this crazy thing, but they have some clear meaning, okay? So what happens, first of all, there's a low capacity, and basically here, low capacity, here, low capacity, right? You don't have that much, a very complicated model if you regularize a lot or if you have a small number of parameters. And so what happens in the low capacity case? Well, like statistics 101 is if you minimize the absolute value loss and you just have one parameter, what you compute is the median, okay? And so that's exactly what this point is here and here. It's just the median, okay? So makes sense, use L1 loss, you get the median. And like Nan was saying, like actually the other guy also has a meaning. So if you're over here in the high capacity case, what you get is just the mean. So it's the minimizer of the squared loss, okay? So this, and then, yeah, actually, you know, income is a heavy-tailed random variable, right? So the mean and the median value of income are actually quite different because there are some people who make like a lot of money, right? So that's exactly what we're seeing here. And okay, so it's kind of interesting because the model you optimize with L1 loss, at least in your code, but then somehow we decide to optimize a different loss instead, right? So that's what I think is like a little bit interesting. And then here's the question which I'm also going to answer. It's like, where did the squared loss come from, right? Like, you know, if this was my training loss, how did it decide to pick this other loss, okay? And then if you think about this for a bit, I think there's a natural answer, especially based off this plot. Where did the squared loss come from? Well, you used a ridge regularization. Ridge regularization has L2, right? So it's got the norm squared. So it's natural to think, okay, that's why this happened. It's because, well, that's not fully explaining what's happening, but it's a natural guess to think this square is like kind of related to the other square. But it doesn't really explain why you would then see the same phenomena as you vary the number of parameters, okay? So there's something missing in this explanation. And it turns out, although I did not do this experiment, if you use an L1 regularization, like a lasso instead of a ridge, you would actually get the same behavior. So yeah, so you could do that at home. And so the L2 actually arises purely from overfitting. So it's just a thing about the model having high capacity, and it's not specific to ridge penalty, okay? And as we'll see, what happens is that just purely overfitting, it transforms the absolute value loss into the what's called a Huber loss, and then ultimately the squared loss. Okay, and so that's, we're gonna go through more in this talk, is this transformation of the loss. Okay, and then yeah, I'm gonna explain the general results now, but they're not that general. Okay, yeah, what I wanna do is understand optimal generalization bounds. Okay, and then kind of the reality of life is, or at least if you do math, is that probably a lot of things are true for a lot of models, but some subclass of models maybe has a nice mathematical structure that we can solve. Okay, so that's a very common thing that happens. And so what I'm going to do is I'm going to make some kind of strong assumptions, but then we're going to get very precise results. Okay, and the key thing that we'll do is we'll assume data is Gaussian. Okay, and then you can do some experiments. Yeah, and like I said, like it seemed like there's some universality. Like it's actually not crucial to assume things are Gaussian. Yeah.
Rationality, or is it some other reason?
No. Like I said, like if you do these experiments, so this is some particular random experiment, but in general, you can do experiments and you change the distribution from Gaussian to other distributions, and like the predictions you get with this kind of methods are robust, so they don't depend on Gaussianity, but the mathematical proof requires Gaussianity with the current technology.
Yeah. In all the experiments, you fitted like the W and the B, right? Like,
yeah, I fit both.
Okay. So that's the only way it makes sense with the.
Yeah.
But then you're just checking the B.
Yeah, I'm just checking the B. Okay, so here are the formal mathematical model, just so we can be precise. So we assume data is Gaussian from normal 0 sigma. And then the label, okay, this one is kind of a minor technical assumption, I think. I'm going to assume the label is generated from what's called a multi-index model. So you have your data, you project it onto like a fixed dimensional space, and then there's some arbitrary transform that goes from the projection to the label y. Okay, so this is like just writing precisely what I said. Yeah, it's called a multi-index model. This model for how you go from the projection to the label y is not going to be related to the loss or anything about how we're fitting the model. So it's just purely a mathematical assumption to make the math work. There's probably could be some way to get rid of this assumption, but at least with the current proof, you really need this. So anyway, the model is misspecified because this could be like a very complicated process, and our results are still going to work, even though we will just be fitting various types of linear models. But this doesn't have to be linear in real life. Okay. And so I thought I would just kind of put the main result onto one slide, but then I think it won't make that much sense. But then we'll explain that it will make more sense. Okay. So here's a key thing which you may have heard of or heard of under a different name before. And this is going to be like the key player in the story, and it's called the Moreau envelope. And so this is the definition. So you have a parameter lambda. Moreau envelope, okay, here I have a second parameter y. You can see it doesn't do anything. I just pass it through here. So it's really a transform of a one input function, and here's the input is y hat. And what you do is the Moreau envelope, you minimize over all u of the function value at u plus a squared penalty. And then this lambda determines the strengths of the penalty. Okay, so if lambda is big, it's very hard to move u very far away from y hat. So it kind of behave like the original function. And if lambda is 0, then this will just output the global minima of the function. Okay, so you might have actually more commonly, I think we talk about the proximal operator, which is just the argument. Okay, so this is the value of this minimization, but the particular u which minimizes it is called the proximal. The output of that's the output of the proximal operator. And we use this all the time. Like in optimization, we have a proximal gradient descent. It's the same proximal operator. Okay, so it's a very just mathematically important thing. And now here's like kind of the main result that we're going to use. So we're going to have this generalization bound, and like promised, okay, it's going to be kind of weird in that the test error is measured. Okay, so here, imagine f is like absolute value loss or something, right? So f is what you're directly training. This part is not a mystery. Generalization bound, you expect training error to appear on the right-hand side. We're also going to have some kind of measure of complexity of the class. It's going to be the Rademacher complexity, which is kind of the standard or most commonly used complexity measure. The exact definition of this, I mean, I'll tell you it, but it's not going to actually play that important a role as long as you can kind of evaluate it. And then, but the really weird part is that the test error is measured with respect to the Moreau envelope. Okay, so the training loss here, test loss here is the Moreau envelope. Okay, and it's like I think someone said, yeah, uniform convergence bound, uniform generalization bound. So it's like you pick a class of functions f, and then that class has some complexity, and this shows up here, and then this bound will hold for all w and b in the class. Okay, so it's a uniform convergence bound basically. And so Rademacher complexity, very standard notion. It's just for the class of functions, how well they can fit random signs. So this is the definition. So you sample a bunch of independent random signs from the hypercube, and then you look at how well your functions can correlate with that. Okay, so that's basically the most standard notion of complexity for a class of functions. Okay, so this is like the main result, but like, yeah, didn't really explain, why are we doing this or what's going on, but like, I try to convince you this is like a really, in some sense, a really good generalization bound. Okay. And so yeah, let's do an example. So the key thing that may be unfamiliar is Moreau envelope. So let's just calculate it out. Okay, so like we were doing before, let's use the L1 loss and let's compute the Moreau envelope. Okay, so you can solve for the proximal operator using calculus. So you set the derivative to 0. Okay, and then basically derivative of absolute value is like 1 or minus 1. And then the derivative of this one is like, linear. Okay, so you do some calculus, and what you're going to get is the minimizer. So the proximal operator is 0 for y hat at most 1 over 2 lambda. And then otherwise, it just outputs y hat minus some small number. Okay, so this operator, it just shrinks things towards 0. Here's a picture. So if you ever did proximal gradient descent, this is probably familiar. This is like the example you always use. Okay, so that's that. And then, well, that's the proximal operator, but maybe you haven't seen the Moreau envelope. The Moreau envelope is another thing which has a name. It's called the Huber loss. Okay, and so it looks like this. So it's just a function. So compared to the absolute value loss, it's become smoother at 0. In fact, it's just a quadratic at 0. But then far away from 0, it's linear. Okay, so that's the Huber loss. That's common loss in robust statistics. And as lambda goes to 0, the Moreau envelope will basically just be lambda times the squared loss. Okay, so that's the example. So now that we calculated the Moreau envelope, we could actually apply this bound. And then, yeah, so that's kind of the story with this example. So I didn't fully explain the connection, I guess, but like, you can certainly apply this bound in the example we saw. Okay, and then you have all these losses. And with the envelope parameter, in some sense, like if you set the envelope parameter very big, it doesn't change the loss that much. You just have L1 loss. As the parameter becomes smaller, you get the Huber loss, like we just saw. And then in the extreme case, you get the squared loss. Okay. And this is Gauss, because supposedly he invented squared loss. I don't know. Okay, and then these ones are the ones we use in robust statistics. Okay, and yeah, they're just saying what I said before, that you can kind of calculate out what happens, and every point corresponds to some value of the envelope parameter lambda. And moreover, if you look at the generalization bound and you plug it in for the right value of lambda and use what I would call the appropriately localized Rademacher complexity, this bound becomes an equality. So it's just to say, in a way that I'll make more precise, that this bound is very tight and understands exactly what's going on in this example when I set the parameter lambda correctly. Okay. So I don't want to spend actually too much time on explaining in what sense this is optimal or tight, but just a little bit of time, explain it at an intuitive high level. So what would it mean for a generalization bound to be optimal, right? So basically what this is going to mean is that like for a natural learning algorithm, so for some procedure which actually outputs a W and B, that this inequality is going to be close to inequality, right? So that's what I kind of mean by saying, oh, this thing is optimal. It's like tight. So the inequality can get saturated. And also there's this phrase localization. And what this means here, again, is not something super complicated or deep. It's just you initially start with some class of functions, and then you apply the bound. But then it tells you something about your predictor, right? So like if you compute the training error and the initial Rademacher complexity, you get a bound on the test error. But that actually means you go from the original class of function to the subset, which actually has good test error. And so when we talk about localization, generally speaking, just means then go back here. This term became smaller, so you get an improved bound here. And then you repeat this fixed point process. So yeah, whenever I say localization, basically just refer to this simple thing. And so when you do that fixed point process, then this bound can become an equality. Okay. Yeah. And so yeah, what you can do is you can rearrange the generalization bound so the training error is the only thing on the right-hand side. Yeah. Yeah, sure.
A little, at least to me, a little subtle. So
Okay.
in order to make this a formal bound that we want to state as optimal, we of course have to move some things to one side and put a soup in there. But with the soup is what we're trying to say is an equality.
Like I'm gonna say like I pick the L1 loss and then I do ERM, right? So I like.
But I'm just saying the thing that turns into the equality is the thing with the soup on the left-hand side, the soup over the W and B. Because you're saying that.
No. Like what? Okay, yeah, maybe. Yeah, what I'm gonna say is like I'm in particular, let's say in real life, I'm interested in the convex. Sorry, I don't know why I use all this jargon. I just like I'm gonna actually do the L1 regression, and like maybe that's the only point I actually care about. And then I'm saying then if I do this correctly, here I'll have the training loss of the L1 regression, and then here I'll have this thing, and this is gonna be equal to this.
This max is capturing this fixed point.
Yeah, and this max is okay. Here, like this is actually a family of bounds, right? Because there's a lambda. So the max is just saying I do this fixed point process for all values of lambda, and I feed all of them back in here.
This holds for all lambda and for all WB, right?
Yeah, so this inequality exactly hold for all lambda WB, and so you get a bunch of information, and then
message something like this is you change lambda, Moreau envelope smooths out the function.
yeah, right.
So if lambda is changed, you can basically say I'm smoothing the function. It ignores the details that have been present during training time.
Yeah.
So it's kind of not it's natural to expect that at some point there's be critical value of lambda after which the test loss has nothing to do with training loss almost because all the detail is gone.
Yeah, although it turns out when lambda gets small, you kind of want to divide both sides by lambda, and that would probably be like there's like some scaling factor. So it's not so like okay, well, just explain like basically this can always be when you write it correctly and you optimize over lambda and so on. This basically become an equality for the training error, so it worked for regardless of the value of lambda, or as long as.
He's a regularizer essentially for the left-hand side.
Yeah, and so like I'm going to explain also some literature that's related to this, but basically you can write down formulas for the training error, which kind of look like this, and then when you use those formulas for the training error and then plug it into the generalization bound, you see that the two sides become equal. Okay. So I won't explain the details of the proof of this. But this is kind of like a phenomenon that happens, and this is what I'm saying. Like mathematically, like when you do these analyses to understand exactly what happens, you see that this Moreau envelope really does show up. Okay, and so here I want to give credit to this big literature. But then if you look in the literature, the results are quite hard to parse. So like I'm not going to explain what it's saying, but basically if you do M estimation in these kinds of settings and you have a bunch of assumptions like the number of variables and the number of samples are proportional, and so on, you can get formulas for things like the training error and so on that are given by Moreau envelope. So it's not our original idea is that like Moreau envelope is really important, but then to put this into generalization theory is the new part, okay? And like just some buzzwords like this. This is one paper by Trampolidis, Abbasi, Hasibi, and then they use this method called convex Gaussian min-max theorem, and then there's like a lot of papers which use this method. But then another buzzword is like there's also approximate message passing. You can also get similar formulas from that. And this is like an example of a paper which developed a theory in a suitably general setting, okay? So it wasn't important to understand all the discussion there, but basically when you actually do the ERM, like this kind of bound actually becomes tight. So that's why I say it's optimal, okay? And now I'm gonna explain some examples, which hopefully will make it clearer. And then this is where this weird idea of Sqrt-Lipschitz loss shows up. Okay, so again, it's not a common thing that people look at, but turned out to be very mathematically natural. So we'll have this weird bound, but it's like a lot easier to use if your loss is square root Lipschitz, which I just mean your square root of your loss is Lipschitz, okay? So this is a weird mathematical exercise you can do. So if you have a function which is non-negative and square root h square root Lipschitz, that's equivalent to this weird property of the Moreau envelopes, that f lambda is at least lambda over lambda plus hf, okay? I don't have a great intuition for this, but it's something that you can easily prove, okay? You just check it. And so what does that mean is that I can replace the Moreau envelope in the previous bound by just a scaled version of the test loss. I could lose something because it's just an inequality, but in many cases it's equality. Okay, and then yeah, now we have this weird thing, and then there was always this annoying lambda. But the great thing about this setting is you can eliminate the lambda. So you just multiply through, you get this bound, and then if you think about like inequalities, there's an optimal choice for lambda. And then when you do that, everything just simplifies. So for the optimal lambda, you get the square root of the test loss is upper bounded by the square root of the training loss plus the distortion from the complexity. Okay, so this is just to say, in many cases, the bounds that look kind of complicated simplify a bit to look like this. Okay.
Yeah. Its relationship with generalization.
Yeah.
I know of at least 3 places it's been rediscovered over the last 30 years in the literature.
Oh, okay, great. Yeah, that sounds good. Yeah.
And specifically at the places where it appears, it is not smoothness. It truly is Sqrt-Lipschitz.
Yeah. Okay, good.
Very weird. And, yeah, I'll tell you.
Yeah, it's also in this talk, it will end up that you get things that are Sqrt-Lipschitz but not smooth. Yeah. All right, but let's start with a simple example. Okay.
Specific to proportional asymptotics, or it's
Yeah, no, it's right. If you look at the results in the paper, it's not specific to proportional asymptotics, but there's a bunch of non-asymptotic correction terms. Yeah, so.
It's the fact that you get equalities for your generalization.
Oh yeah, the fact that you get equalities it's always true in proportional asymptotics. It's also true in some settings outside of proportional asymptotics, but it's not true for like every sample size, every parameter, and so on that you get equality, because that's not possible. Yeah. Okay, so yeah, we start from general and then let's go to simple. It's like the reverse order of how you're supposed to teach, but nevertheless, what I'm doing. So simplest case is a squared loss for a linear model. So then you just get this kind of bound. So the square root of the square loss then was the square root of the square loss for the training, and then plus some random macro complexity. And that actually has a name. It's called an optimistic rate bound in generalization theory. And it turns out this kind of inequality is very tight for squared loss regressions. Okay. So just an example. So like here, like I did a linear regression and I used data which is normal 0 ID. And there's some noise and there's some ground truth signal. And yeah, we don't need to explain all the curves in this plot, but basically there's this one orange curve, which is the true test error. There's like the blue curve, which is the training error, okay, which is all the way down here. And then there's the local, there's the generalization bound suitably localized, which is the red curve. You see it's not equal to the test loss, but it's very close. And yeah, when you take dimension, number of samples big, they would become equivalent, okay? So just an example to illustrate, yeah, this kind of bound is like really tight, okay? And yeah.
So the first squared loss, I assume that result is known to like Kosinski or like the localization for squared loss giving you that type.
Oh yeah, that it gives a tight thing. It's in this paper.
Is there an older reference or is it?
Well, it's kind of like an interpretation of what happens when you apply CGMT or AMP. So in that sense, like,
Okay.
yeah, like when you do CGMT or AMP, you get all this formula involving proximal operators. And then if you think about what they mean, it can be equivalently rephrased. The way I said in terms of fixed point argument and local random macro complexity, but that's not how people normally phrase it. Yeah, but if you think that's like the formula is the same. Yeah.
So where's the connection to AMP? This is like the fixed point argument that you're running. Like that's kind of like an AMP.
No, that's not the connection. Is that okay? We go back here. Like we know Moreau envelope shows up because when you really analyze what happened with M estimation, you get Moreau envelope. And then, okay, since you know what AMP is, it makes sense also to derive this with AMP. And that's actually, I guess, the original motivation for AMP. And then with AMP is kind of like proximal gradient descent. So it actually makes sense for AMP why you get Moreau envelopes. If you don't know what AMP is, it's fine. It doesn't matter. Okay, so yeah, we get this generalization bound. Yeah, it was. Yeah, this was the focus of some previous work. So this is a publication year with a journal, so it's a lot of years after the original paper. Yeah, and then yeah, one reason that back then we were studying this is people were really interested in benign overfitting. Then this is another example. So this is a case where here, like I'm setting my rich parameter to 0, and like I'm overfitting a lot, but this kind of bound is very tight and can understand the fact that even though you're overfitting, your generalization score is good. Okay, yeah.
Both has an upper and a lower bound, and has these like capital R.
Oh yeah.
So with this like generalized Moreau envelope approach, you think you can get the same sort of.
Yeah. So I mean, in some sense,
like the tight aspect. It can recover the tight aspects of that.
Yeah, so for us, like we just proved the upper bound, but there's a bunch of works actually by Fanny Yang and other people where they use the same technique to prove lower bounds. So you probably could prove everything. Compared to other methods, this method is a little special to Gaussian. Like, so you can use random matrix theory, and then it's not so specific to Gaussian. But yeah. So I think it's possible to do all those things, but we didn't do all. Yes, I don't want to spend a ton of time on banana overfitting, but it's just like we know if your matrix has a lot of little eigenvalues, and even if you interpolate the data and it's noisy, you'll converge to an oracle, which is the performance of the squared loss. Okay, so that's the whole story of banana overfitting in like one slide. Okay, and then you can recover this from this bound using norm bounds and so on. So I don't want to go into too much detail on this because it's like a whole other talk. And actually, there's a recording. I gave a talk on this at Simon's Institute. So if you really are excited, you can watch that talk and it would be much clearer. But yeah, the high level is like, yeah, we know this kind of bounds are really tight. And in general, they involve the envelopes. In the special case of square loss, it just comes down to the square root thing. Another case, you can look at classification. The analog of square loss turned out to be squared hinge loss. Okay, so that's one of the common, but not most popular loss for classification. But if you interpolate data and like compute the max margin, and then you're like, and you have a high capacity, so you overfit, this squared hinge loss is kind of the natural analog of squared loss for regression. And yeah, you can generalize benign overfitting from regression to classification if you use this squared hinge loss. And in fact, you can use one proof that captures both. So yeah, just to say, in classification, just like L1 to L2 was a story in regression, if you use hinge loss or logistic loss, as you overfit, it starts to transform into this squared hinge loss. Okay. Now, okay, I think I don't want to blow too much time before I get to the last part. But just to say, like, yeah, when you start to care a lot about generalization theory and say you want to really understand what happened for LAD, you realize, yeah, this Moreau theory is like really improve something over the classical generalization theory. So if you use a contraction principle, this is a Lipschitz loss. So this is like a standard generalization bound. The test error under L1 is the most train error plus twice the Rademacher. Turns out if you have Gaussian data, you can kill the two. So you can bound this by the Rademacher. And you can also prove that that constant is tight if I put a 1 there. Okay, so you can work out the optimal generalization bound of the usual form. But then, yeah, what happens, and so I'm not going to show all the calculations, but there's a paper, is that, yeah, if you do LAD and you have the benign overfitting conditions, so this is just some example of a covariance matrix that has a lot of small eigenvalues, then LAD is consistent. So what's the L1 loss become? It becomes the absolute value of a Gaussian, which is the noise. There's like 0.798 times the variance standard deviation sigma. Okay, if you were to use the best possible bound of this form, which is this, it turned out you can only guarantee performance of sigma instead of 0.798 sigma. It has to do with the fact that if you look at the best possible bound of this form on a norm ball, it's saturated by points which have large training error. And then the Moreau envelope, the parameter lambda is actually related to, like the lambda that you should pick is related to the capacity, it's related to the overfitting. And so like the Moreau envelope theory can produce the correct generalization bound for the low training error case. Okay, so that's, I think I went really fast over this, so it's fine if it's not super clear, but yeah, it's kind of like, yeah, there's really a benefit to looking at bounds of this different form.
Thank you, this is so cool. I think someone asked something very close to this right before, but is the Gaussian assumption that we need related to the fact that we're using L2 regularization, like if we're using L1 regularization?
Oh no, yeah, this. Yeah, there's like, okay, using this technique, you can get really good results for lasso as well with Gaussian data. It's just, yeah, the proofs are always more complicated, but they've been done.
Like, is it related to the prior that the regularization assumes? Like,
no, because the coefficient vector, we don't assume anything about its structure.
Okay.
And then this Gaussian is unrelated to all the other Gaussians. It's just because I assumed a Gaussian model for the noise. Okay.
You use the multi-index model here?
Yeah, so the multi-index model is really technical detail. Like, I want to study misspecified models, so I don't really want to assume any relation between y and x. But to make the proof work, we need to assume a little bit. So y is generated by an arbitrary process that looks at a low-dimensional projection of x. It just shows up in the proof. Yeah.
The low dimensional stuff, like the dimension of that shows up, or no, it's not important.
The dimension of the projection shows up. Yeah, but conjecturally, like all the results are true just for any relation between x and y, but like mathematically, we currently need that. And it's a common thing that, yeah, with these techniques, they kind of like that assumption. Yeah.
For the square laws, how does this relate to this offset Rademacher complexity thing?
Well, offset Rademacher complexity is just a different way to look at localized Rademacher complexity. So
Is there like a direct way we can connect these systems, or only through the localized?
no, I mean, okay. We look at conceptually, there's not really a difference between offset and localized Rademacher complexity. If you look at these kinds of formulas, they kind of look more like offset Rademacher complexities, just like at the technical level, like there some min-max optimization. So yeah, at a technical level, when you do these things, you get something that looks more like offset Rademacher complexities, but they're all equivalent.
So, because you were saying there was a question about it. Someone was asking if it actually follows from the old paper by Peter on local, and you were saying, so while you're saying they're equivalent, they get equivalent results. But in terms of the actual steps of the proofs you're writing, the steps of the proofs you're writing look more like offset Rademacher than like actual localized Rademacher, right?
I guess, okay, there are a lot of papers. There's like the results on benign overfitting for linear regression. Those are usually use random matrix theory methods, right? They don't really use Rademacher complexity at all.
But I thought part of your goal was to actually try to invoke a standardish tool.
Yeah, so we prove the generalization bound using different techniques, but clearly the terms in the bound, one of them is Rademacher complexity, right? So it's not the standard Rademacher complexity bound like the Bartlett, Mendelssohn or whatever, because that one's not very sharp. But we just prove a different bound. But the key quantities that show up are the same. They're Rademacher complexities.
You don't then think it's completely fair to just call it an offset Rademacher complexity?
No, they are local Rademacher complexities, but it's not the result of the paper titled local Rademacher complexity, right? And like, yeah, the offset and local, they're basically sound. It's just a technical detail of how you arrange them. Let's see, where were we? Okay, yeah, you can use this bound. They're really tight. Yeah, so on. Now we're fitting complication. Okay, I think we were here. So yeah, what's become more interesting, a little more fresh, and it's basically where I want to end, is the case of a ReLU regression. Okay, so yeah, we do all this stuff for linear model, and people are like, oh, linear model, okay, it's good, but like, what if it's like a little more complicated than linear model? So let's do a little more complicated than linear model, ReLU regression. Okay, and so we saw for linear regression, and as you overfit more, you naturally converge to, or your oracle is a squared loss oracle. So now we can ask the same thing, but let's do it like with a ReLU neuron instead, okay? And it's just, it's kind of a natural thing to do. So here, sigma is the ReLU function, and I'm gonna interpolate with this guy instead, okay? And so like, yeah, you're like, okay, I can pattern match, like the thing you should get is like the model which minimizes the squared loss, okay? So that's pattern matching. But pattern matching is wrong. So for various reasons, actually, you can figure out, okay, there are simple arguments to prove this loss is wrong, but I'm not gonna explain those. I'll just tell you what's the correct loss. The correct loss is it's a discontinuous actually. So it's a function of y and y hat. So it's not discontinuous in y hat, but in y it's discontinuous. So if I interpolate data with a high capacity ReLU neuron, and I have benign overfitting conditions, I converge. My oracle is the minimizer of this loss, which if the true label is bigger than 0, it's the squared loss of the pre-activations. So the y hat is the number, wx plus b, before applying the ReLU. And if y is 0, it's sigma y hat squared. So if y equals 0, this is the same as this. But if y is bigger than 0, it's actually a different loss, okay? So, and yeah, it's not easy to guess this without just working it out. But yeah, you can do it. And like, this is actually the thing you're going to get, okay? There's a simple reason it's discontinuous, which is, well, it has to do with the fact ReLU is not smooth. Basically, like imagine my goal is to interpolate the data, and then y hat is minus 100 and y is 0. Then sigma y hat equals y, so I'm done, so I don't need to put any effort in. But if y is 0.001, they're not equal. So if I want to interpolate, I need to put a lot of effort to change my prediction on this example. And so that's exactly why you get a loss which is discontinuous. And like Matus mentioned, yeah, this is a Sqrt-Lipschitz, but it's not smooth. Okay, so the second derivative doesn't exist at 0. Okay, so yeah, Sqrt-Lipschitz is really the correct thing. Okay, there's a lot of interesting things about this. So the loss is not just a function of the model output, but also depends on the pre-activation, the number you put in before the ReLU. And it shows us that whatever this phenomena is, the model architecture actually seems to play a role, even though the regularization schema does not. Okay, and we also solve what happened for a similar model of phase retrieval. In that case, you actually do get squared loss. This case is a non-convex problem. So you might think you can't use these techniques, but actually we can figure out how to work it. Okay, how much time do I have left? 10 minutes. Oh, I have way too much time. Okay, so yeah, I thought with the remaining time, I would tell you a bit about the proof. But then, it's a funny thing. Like the proof is not, maybe it's not intuitive, but it's not very long. Okay, and this is a common property of a lot of argument based off Gaussian min-max theorem, or also known as Gordian's theorem. And yeah, it's also an interesting historical thing. Like this kind of famous paper studying convex geometry or like analysis, high-dimensional geometry. This is one of the papers by Gordon, Gaussian processes and almost spherical sections of convex bodies. And then if you think about it, the spherical thing, it's kind of related to why we have these like L2 things showing up. Okay, so in high-dimensional geometry, that happens. Anyway, yeah, I thought, okay, I mean, I can show you the proof, and then you can decide if it explains anything or not. So the way the proof works is you view generalization. What is a generalization bound? Really, it's just a way to lower bound training error. Okay, so I just rearranged the inequality, and now it's a lower bound on the training error, and let me try to prove that. Okay, so for simplicity, it doesn't change any of the details of the proof. Let's suppose y is pure noise and there's no intercept to fit, but the proof is almost exactly the same if you include those. Oh, shoot, the animation is, okay, this is backwards. So yeah, so we just want to, I want to prove this inequality. So I want to prove this is at most this. So it's the same as proving the max is at most 0, okay? So that's the way I'm going to structure the argument. So I want to evaluate this max over all w of the gap between the right and left-hand side of the inequality, and say it's at most 0. Okay, so let me scroll back. So this is the second line. So I just use a Lagrange multiplier. Interestingly, this is like a technique that you need to do. It's not clear what the meaning of it is. But before I had this was the original expression where u is equal to xw. And then just for purely technical reasons, I introduced a Lagrange multiplier for the constraint u equals xw. And so this is a Lagrange multiplier. So this is the same as the previous thing, which is now hidden. Okay, and then once you have this, like it's all just automatic. Like you use this Gaussian min-max theorem, and you get this. Okay, so what's going on? What's going on is that originally you had a problem with a random matrix X. So X is a matrix where the rows are independent high-dimensional Gaussian vectors. Kind of hard to analyze this problem. The amazing thing about this theorem is it becomes a much easier to analyze problem. And the idea of the Gaussian min-max theorem is that although random matrices are hard, you can replace them with random vectors. I guess it's like, what's the idea is that like random matrix has a lot of degrees of freedom. It has a lot of randomness. So even though on the left-hand side in this optimization, you have gamma, on the right-hand side, you have w, and you might be really worried about the way w and gamma interact. It might be really complicated. Because things are really high dimensional, maybe it's actually not complicated. And so maybe actually it basically behave like the random matrix kind of behave like two independent random vectors, one that affects things on the left, and then one that affects things on the right. So here, G and H are two standard Gaussian random vectors. And yeah, the Gaussian min-max theorem is exactly saying you can replace this guy by this guy. Inequality is in the sense that any high probability upper bound on this guy is a high probability bound on that guy. Okay, and yes, from here, like you really just will have to do the calculation, I guess, right? So I just combine terms which have the same gamma. I get here, okay, and then I can interpret this gamma as like actually a Lagrange multiplier. So before I like randomly introduce the Lagrange multiplier, now I unintroduce it. And so if you think about what this means, you have this constraint. So it's just this is the Lagrange multiplier version of this optimization. Okay. Yeah, like I said, it's not clear how insightful these proofs are, but then they work and they give you the correct answer. So you have this max, and then yeah, you have this quantity, which is like the difference between u. So originally u was xw, but now we're in this different world where x doesn't exist. There's just Gaussian vectors, so it's not entirely clear what u means. And u is constrained to be close to a scaled version of h. So I'll call r the difference, and then I rewrite it. Okay, so this is just this, where I let this minus this be r. Okay. And then, obviously I could add and subtract the same number. So plus lambda r squared minus lambda r squared. And the reason I do this is because there's like a lambda something squared in the Moreau envelope. So if I want to get Moreau envelope, maybe it's a good idea to try to push it in there. Okay. Okay, so we're here. We can upper bound this by breaking apart the min. So yeah, if I break apart the min, it just makes it bigger. Okay, so I get this guy, and now it's looking really promising because this looks like a Moreau envelope. And this guy actually, if you think about it, it looks like a Gaussian width or random macro complexity. So then you can put in the definition of Moreau envelope. Okay, and now we're looking like we're basically done. This thing is actually just the random macro complexity squared. I have a slide which proves it, but it's not surprising. Interesting. And so you proved inequality. Okay, so like, you didn't need to follow all the steps of the bound, but like you can see it's true and like it works. And yeah, if you know like enough weird math theorems, like you can prove like some pretty interesting things, right? I don't know, that's the moral, right? It's like math is one world, and like some things are easy in math, even if they're not that intuitive. And then some things are intuitive, but not that easy in math. Okay, so here it's like kind of easy in math, but not necessarily intuitive. Yeah, you can easily calculate. So I just did this out here. Like this is the random macro complexity, but Gaussians are sign symmetric. So that's basically why if you have this maximization involving a Gaussian vector, it ends up to be the same thing as random macro complexity. Okay, so yeah, I think we're pretty much done. So closing thoughts. Yeah, this is a high-level message that it seems when you have some amount of overfitting, which is often good for getting the best test performance, there is this weird phenomena where your test loss may not really be quite the same as a train, or maybe it's better to look at a different test loss. Another weird thing that happened in this example, which is maybe a bit specific, is that we saw L1 loss can become replaced by the L2 loss when you overfit. So that means, yeah, just overfitting caused the model to care more about outliers, which is neither a good or bad thing, but it's kind of a strange, interesting thing. And then, yeah, higher level point, yeah, you trained a model with one loss, but then because of all these things going on, like even though you told it, oh, do this, like compute the median, actually, because all the other factors in your training actually decide to compute the mean. So it's a case where you tell the model to do one thing, but it does something else, right? Which is always interesting. There's probably more to say if you look at more complicated models, but it's just what we understand today. And yeah, so probably we should do some more work, but that's all we have today. Okay, thanks.
You mentioned that you have a way of extending the CGMT framework beyond to settings which are non-convex. Can you say a little bit about that?
It's not that we have some general way to extend it. It's that, well, first of all, like the CGMT, it's basically apply Gaussian min-max in two directions. And then in this direction, which is what we applied, this actually doesn't rely on the convexity. So Gordon's theorem doesn't need convexity. But then the CGMT framework needs convexity because we want to prove equalities, right? And so if you want to get the other direction of the inequality, you need convexity because you need to apply the normal min-max theorem and then apply Gordon's theorem again. And what happened is that in some cases, even though this is not a convex optimization problem, we can come up with a direct proof basically of the, okay, the proof still, I think we do end up using Gordon's theorem, but there's probably other ways to do it. So if you can come up with a different way to prove the other direction of the inequalities, then you're done. But it's not that so the generalization theory, there's no assumption of convexity. That's always general. Getting the other direction, we just, in that case, there's a direct way to do it because we can kind of guess intuitively what the properties of the optimizer are. Yeah.
Is the loss that you got for the ReLU the matching loss for ReLU?
No, it's not. Yeah, it's because that one will, I think among other things, be continuous, and this one is not continuous. Yeah.
What's that continuous?
Since the generalizations are related to like the square root of the loss, would the solution also be related to like a square root type of loss, like square root method, let's say square root maximum or something like that?
Yeah, that's right. There is some connection in the sense that
Like, is it asymptotically similar or like?
well, yeah, it's just like one way to maybe quote unquote derive squared lasso would be like, oh, this is like a really good generalization bound, and then I can upper bound the Rademacher complexity by the L1 norm, and then that would give me a right-hand side which I could optimize, and then that optimization problem is the square root lasso if I upper bound Rademacher complexity by L1 norm. So that is a connection, is that square root lasso sort of optimize the right-hand side of this generalization bound. Yeah, I don't.
Right, but like the solutions of like, let's say initially you do like square root lasso, like your problem,
Yeah.
you just like write it down as fixed by yourself. Would the solutions like correspond to the L1 norm? Sorry, L1 loss that you initially had?
Oh, this whole thing with square roots is specific to. I pick the training error to be a. Well, I pick the training error to be square root Lipschitz. So in this case, I pick training error to be squared loss. In which case, like this right-hand side is like, yeah, it look like. Well, yeah, there won't be any L1 loss.
Again, this is so cool. Would this methodology extend to like kernel ridge regression, or if you like?
Yeah, so this is like it's a universality picture. Like if you read statistical physics papers, they're just like, let's analyze kernel ridge regression. We just assume that when you do kernel ridge regression, everything just behaves the same as Gaussian case. Okay, so and then actually they get pretty good results. Like they seem to match the predictions pretty well, but that's not mathematically rigorous. And then there's also works to prove universality. But yeah, the short is that at least rigorously it doesn't apply to kernel ridge regression because the features are not Gaussian.
Gotcha. Thank you.
Okay, let's thank Fred again. We'll be back at 10:20.